Good afternoon, dear children. We can continue the lesson work, energy, and power. Okay, last class we have discussed about the law of conservation of mechanical energy, and that can be applied to a freely falling object. Okay, law of conservation of mechanical energy that can be applied to a freely falling object. And also we have derived an expression for potential energy. Also, we have derived an expression for elastic potential energy and a gravitational potential energy. Listen it. And today's class we can discuss about the different forms of energy. You know what are the different forms of energy? I think you know. We have the mechanical energy, then internal energy, then chemical energy, then electrical energy, and nuclear energy, and thermal energy. These are some of the forms of energy. I think you know. Isn't it? What are the different forms of energy? Mechanical energy, internal energy, then heat energy, then chemical energy, then electric energy, and nuclear energy, etc. are the different forms of energy. Listen it. Next we can talk about Einstein's mass energy relation. Einstein's mass energy relation. Okay, Einstein's mass energy relation. Actually, Albert Einstein showed that mass and energy are equivalent. Okay, and these are equivalent. That is, mass and energy are equivalent, and he found out a relation connecting these two. That is E equal to mc square. Okay, this is actually Einstein's mass energy relation. E equal to mc square. E equal mc square, where actually m represents the mass of the object and c actually the speed of light. Okay, c represents actually the speed of light in vacuum. Okay, c represents the speed of light in vacuum. Actually, its value is 3 into 10 power 8 meter per second. Okay, 3 into 10 power 8 meter per second. Okay, and actually if the mass of the object disappears and the amount of energy E equal to mc square appears in some form. Listen it. Suppose if mass is disappears, the equivalent amount of energy, that is E equal to mc square, that appears in some form. Okay, conversely we can say when the energy E disappears, then the mass m equal to E by c square that will appears. Listen it. If the energy E disappears, then an equivalent amount of mass m equal to E by c square is appears. Okay, that so we can say the mass and energy are actually equivalent. Okay, mass can be converted in energy and vice versa. This is actually Einstein's mass energy relation. Listen it. Albert Einstein showed that mass and energy are equivalent, and we can relate these two by the relation E equal to mc square. Actually, this is Einstein's mass energy relation, isn't it? Where m is the mass of the object and c the speed of light in vacuum. Actually, its value is c equal to 3 into 10 power 8 meter per second. Listen it. Actually, if mass disappears, then energy E equal to mc square that appears as some form. Okay. Conversely, we can say if energy disappears, then mass m equal to E by c square is appears. Isn't it? That about Einstein's mass energy relation. Next, we can talk about the principle of conservation of energy. Principle of conservation of energy. Okay, principle of conservation of energy. Okay, actually this thing you already learned in lower classes. What is actually the principle of conservation of energy? Energy can neither be created nor be destroyed, but it can be transformed from one form into another form. Okay, energy can neither be created nor be destroyed, but it can be transformed from one form into another. That is actually the principle of conservation of energy. Okay, what is actually the principle of conservation of energy? Energy can neither be created nor be destroyed, but it can be transformed from one form into another. Okay, actually we already proved the principle of conservation of energy for a freely falling object. That thing can be taken as an example for what? the principle of conservation of energy. There we have proved them when an object falls to waste earth at any point, we can prove the total energy that remains constant, where actually the transformation of energy occurs, that is the conversion of kinetic energy into potential energy and potential energy into kinetic energy. Okay, that is actually the principle of conservation of energy. Energy can neither be created nor be destroyed, but it can be transformed from one form into another form. Okay. Next we can study about power. Okay, we can talk about what power. Actually, it is the rate of doing work. Power means actually a rate of doing work. Okay, the rate of doing work. Suppose if an object does W work during the time T, then the power, the average power can be written as P average is equal to work by time. Okay, work by time, that is equal to W by T. Okay, this is actually the average power. Isn't it? Actually, it is the rate of doing work. Power of an object is defined as the rate of doing work. Suppose if an object has done work W during the time T, then its average power P average equal to work by time or W by time. W by T. P average equal to W by T. Isn't it? And here the power is a scalar quantity. Power is actually a scalar quantity. Power is a scalar quantity and its unit is actually watt. Its unit is watt. Okay, what is the power? What is the SI unit of power actually? Watt. Watt is the SI unit of power. Listen it. Okay, what is actually power? The rate of doing work. Power is defined as the rate of doing work. Okay, suppose if an object does work W during the time T, then its average power P average is equal to W by T. Isn't it? Then actually power is a scalar quantity. Power is a scalar quantity and its SI unit is actually watt. Okay, watt is the SI unit of power. So using this equation, we can define 1 watt. That is 1 watt is equal to 1 joule by 1 second. 1 watt is equal to 1 joule by 1 second. Actually, power is said to be 1 watt if an object does work at the rate of 1 joule per second. Okay, if an object does work at the rate of 1 joule per second, then the power of that object is said to be 1 watt. Listen to it. Define 1 watt actually. If an object does work at the rate of 1 joule per second, then the power of an object is said to be 1 watt. Listen to it. Then we can use kilowatt and horsepower are the bigger units of power. Kilowatt and horsepower. Kilowatt and horsepower are the bigger units of power. That is 1 kilowatt. 1 kilowatt is equal to actually 1000 watt. Okay, 1 kilowatt is equal to 1000 watt and 1 horsepower equal to 746 watt. 1 horsepower is equal to what? 746 watt. Listen to it. Here, actually power, what is power? Power is defined as the rate of doing work. Suppose if an object does work W during the time T, then its average power P average is equal to W by T. Then power is a scalar quantity and its SI unit is watt. Then what is actually 1 watt? 1 watt is equal to 1 joule by 1 second. Okay, the power of an object is said to be 1 watt if that object does work at the rate of 1 joule per second. Then what are the bigger units of power? That is kilowatt and horsepower are the bigger units of power. That is 1 kilowatt is equal to 1000 watt and 1 horsepower equal to 746 watt. Next about the instantaneous power. Next about what? The instantaneous power. Okay, you know the power of an object may not be a constant during a time interval. Okay, the power of an object may not be constant during a time interval. So we have to calculate the instantaneous power. Okay, you know the instantaneous power is actually defined as the limiting value of average power when the time interval approaches 0. Okay, suppose if delta W be the work done during a small interval of time delta T, isn't it? Then the instantaneous power P is equal to limit delta T tends to 0 delta W by delta T, and which is equal to dW by dt. This is actually the instantaneous power, isn't it? Here the instantaneous power is defined as the limiting value of the average power when the time interval approaches 0. When the time interval approaches 0, and this can be expressed as limit delta T tends to 0. Limit delta T tends to 0 delta W by delta T, that is actually takes the form dW by dt. Listen it. The instantaneous power is defined as the limiting value of average power when the time interval approaches 0. It is the limiting value of average power when the time interval approaches 0. Here let delta W be the work done during a small interval of time delta T. Then the instantaneous power P can be expressed as P is equal to limit delta T tends to 0 delta W by delta T, and which takes the form dW by dt. Okay, that is about the the instantaneous power, isn't it? Actually, instantaneous power is defined as the limiting value of average power when delta T, when the time interval approaches 0, and this can be expressed as P is equal to limit delta T tends to 0 delta W by delta T, and which is equal to dW by dt. Okay, next we can study about the power as the dot product. How we can express power as the dot product. Okay, we can express power as the dot product. You know, the work done by a force F. Okay, the work done by a force F for a small displacement dr. For a small displacement, dr is actually given by dW is equal to F dot dr. That thing you know, work done can be expressed as the dot product of force and displacement. Okay, work done can be expressed as the dot product of force and displacement. Here, let F be the force and dr be the displacement. Then the work done dW can be expressed as F dot dr, isn't it? The next we can express the instantaneous power. That is the instantaneous power, you know, P is equal to dW by dt. That is the instantaneous power. Power P is equal to dW by dt. Okay. Then what is actually dW? F into dr. F dot dr, that divided by dt. F dot dr by dt actually here. You know, but dr by dt. dr by dt is actually the rate of change of displacement, that is the instantaneous velocity v. dr by dt is the rate of change of displacement, which is equal to the instantaneous velocity v. Therefore, P can be expressed as F actually here. Then instead of dr by dt, we can write velocity v. So, the instantaneous power can be expressed as the dot product of force and instantaneous velocity. Okay, the instantaneous power can be expressed as the dot product of force and velocity, that is P is equal to F dot V. Simply we can say power can be expressed as the dot product of force and velocity, that is P is equal to F dot V. The power P is equal to F dot V. Listen, it is a very very important relation. Power as the dot product of force and velocity. We can express power as the dot product of force and velocity, that is P is equal to F dot V. Listen to it. Here we are considering a force F that causes a displacement dr in an object, and the work done by the force dW is equal to F dot dr. Then the instantaneous power P is equal to dW by dt. Then instead of dW, we can write F dot dr, then divided by actually dt. And here dr by dt, that represents the rate of change of displacement, which is actually the instantaneous velocity v. So P equal to, we can write F dot v. So the instantaneous power can be expressed as the dot product of force and instantaneous velocity, that is P is equal to F dot V. P is equal to F dot V. Okay, all of you got it? the next we can talk about on unit actually kilowatt hour. Kilowatt hour. Actually, the joule is the SI unit of energy. That joule is the SI unit of energy. Suppose if you want to measure a large amount of energy and this unit is not actually sufficient. So in order to measure energy commercially, we can have another unit that is actually the kilowatt hour. Okay, so we can say kilowatt hour is the commercial unit of electric energy. Which is the commercial unit of electric energy actually? Kilowatt hour. Kilowatt hour is the commercial unit of electric energy. Okay, kilowatt hour is the commercial unit of electric energy, and we can define 1 kilowatt hour is the electric energy consumed by a device of 1 watt, device of 1000 watt in 1 hour. Okay, 1000 watt in 1 hour. Listen it, 1 kilowatt hour is the electric energy consumed by a device of 1000 watt in 1 hour. Okay, what is actually 1 kilowatt hour? It is the energy consumed by an electric device of 1000 watt in 1 hour. Okay, and we have a relationship between kilowatt hour and joule. That is 1 kilowatt hour is equal to 3.6 into 10 power 6 joule. Okay, 1 kilowatt hour is equal to actually 3.6 into 10 power 6 joule. That is about the relation between kilowatt. Actually, that is the relationship between kilowatt hour and joule. Okay, actually kilowatt hour is the commercial unit of energy or commercial unit of electric energy. You can say that is kilowatt hour, and 1 kilowatt hour is the electric energy consumed by a device of 1000 watt in 1 hour. Listen it, and we have a relationship between kilowatt hour and the joule. So 1 kilowatt hour is equal to 3.6 into 10 power 6 joule. Isn't it? Next we can talk about collision. Okay, how we can say a collision is occurred or happened. Okay, actually a collision is said to occur between two bodies either if they physically collide each other or if the path of one is affected by the force exerted by the other. Okay, a collision is said to occur between two bodies if they physically collide against each other, that is physically hit against each other. That way we can say a collision is said to occur. Okay, a collision is said to occur between two bodies either if they physically collide against each other. If they physically collide against each other, or if the path of one is affected by the force exerted by the other object or other one. Okay, if the path of one is affected by the force exerted by the other. Actually, the collision, for a collision to take place, the actual physical contact is not necessary. Isn't it? For a collision to take place, the actual physical contact is not necessary. Okay, a collision is said to occur between two bodies either if they physically collide against each other or if the path of one is affected by the force exerted by the other. Isn't it? And for collision to take place, the actual physical contact is not necessary. Isn't it? And here we have two different types of collision. First is the elastic collision. Okay, we can have the elastic collision, and second is the inelastic collision. Inelastic collision. We have two types of collision, elastic collision and inelastic collision. Okay, first we can talk about what elastic collision. Elastic collision. Actually, if there is no loss of kinetic energy, during collision, it is called elastic collision. Okay, if there is no loss of kinetic energy during collision, then that type of collision is called elastic collision. Listen it. If there is no loss of kinetic energy during collision, this type of collision is called elastic collision. Then what are the characteristics of elastic collision? Actually, in elastic collision, actually momentum is conserved. Okay, that is the first characteristic or first property. Momentum is conserved. Then its total energy is also conserved. total energy is conserved, and third one, the kinetic energy is conserved. Okay, first is the momentum is conserved during elastic collision, then its total energy is conserved, also kinetic energy is conserved. Then the fourth is the force involving the collision between two bodies are actually conservative in nature. Conservative in nature. The force involving during the collision is actually conservative. And here the next is the mechanical energy is not converted into light energy, heat energy and sound energy. These are the important characteristics of elastic collision. That is, the momentum is conserved, then total energy is conserved, then its kinetic energy is conserved, and the force involving elastic collision is conservative in nature. And fifth one is the mechanical energy is not converted into heat, light and sound energy. These are the important characteristics of elastic collision. Then what are the examples for actually elastic collision? The collision between subatomic particles, that is proton, neutron and electron. Okay, the force between subatomic particles and the collision between the subatomic particles and the collision between glass balls are examples for elastic collision. Okay, that is actually about the elastic collision. Okay, in elastic collision actually there is no loss of kinetic energy. Then what are the important characteristics of elastic collision? The momentum is conserved, then total energy is conserved, then kinetic energy is conserved, and force involving elastic collision is actually conservative, and the mechanical energy is not converted into light energy, heat energy and sound energy. Then the collision between subatomic particles and collision between glass balls are examples for elastic collision. Okay, then what is actually collision? A collision is said to occur between two bodies either if they physically collide each other or if the path of one is affected by the force exerted by the other. That is actually collision. Next we can talk about the second type of collision, that is actually inelastic collision. The second type of collision is inelastic collision. Actually, if there is a loss of kinetic energy during collision, it is actually inelastic collision. Okay, in inelastic collision, there is a loss of kinetic energy during collision. During inelastic collision, there is a loss of kinetic energy. Isn't it? Then what are the important characteristics of actually inelastic collision? The first is the momentum is conserved. Here also the momentum is conserved and total energy is conserved. Okay, here the momentum and total energy are conserved, but kinetic energy is not conserved. Okay, here the kinetic energy is not conserved and the force involving collision are actually non-conservative in nature. Force involved in inelastic collision is actually non-conservative in nature. Actually here a part of mechanical energy is converted into light, heat and sound energy. Listen, these are the important characteristics of inelastic collision. Here the momentum is conserved, total energy is conserved, but kinetic energy is not conserved, and the force involving during collision, inelastic collision is actually non-conservative in nature. Then a part of mechanical energy is converted into heat, light and sound energy. Then what are the examples of inelastic collision? Actually the force between two vehicles, the collision between two vehicles and the collision between a ball and floor. Okay, collision between two vehicles and collision between ball and floor are examples for inelastic collision. Listen it, in inelastic collision there is a loss of kinetic energy. Okay, in inelastic collision there is a loss of kinetic energy. Then what are the important characteristics of inelastic collision? Here the momentum is conserved, then total energy is conserved, but kinetic energy is not conserved. And the force involving inelastic collision are actually non-conservative in nature. Then a part of mechanical energy is converted into light, heat and sound energy. Then examples for inelastic collision is actually collision between vehicles and collision between ball and floor. Okay, that is about inelastic collision. Okay, today's class we have learned about different forms of energy and also we have learned the Einstein's mass energy relation, that is E = mc². isn't it? Then we talked actually the law of conservation of energy. That is, energy can neither be created nor be destroyed, but it can be transformed from one form into another. Isn't it? Then we learned about power. What is power actually? It is the right of doing work. Okay, power is the right of doing work. Then what is the equation for power? P is equal to W by T. Okay, actually power is a scalar quantity. Power is a scalar quantity and its SI unit is actually joule. Okay, then we can express power as the dot product of force and velocity. Okay, we can express power as the dot product of force and velocity. Then we learned about collision, and we have two types of collision, that is elastic collision and inelastic collision. Okay, okay children, that is the end of today's class. Thank you.